From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. So you have homework due today. And over here on my left side, we have some old homework and exams and various stuff I'm trying to clean out of my office. So if you pick it up after class, I'd appreciate it. I guess we start off with the most important item, which is, who do we play in basketball tonight? Cal. Cal? Oh, USC. Okay, good, good. Very good. Okay. And Saturday, who do we play? UCLA. And then what happens on Sunday? You do your homework with that. And they have the selection for the NCAA tournament, I guess, is what is actually happening on Sunday. Anyway, last class we were talking about diffraction. And right at the end of the class, we got to the integral theorem of Helmholtz and Kickoff. So let's write that down again. And remind you that we're following Goodman's book very closely. So if you brought Goodman's book to class, you probably don't have to write down too much here, because essentially everything we're going to say today is in his book. So we had the expression right at the end of class that u of p naught was 1 over 4 pi, the integral over this surface, which we'll soon worry about, partial of u respect to n, e to the I, k, r01, r01, minus u, partial with respect to n, of e to the I, k, r01, oops, need to get that in the field of view here, divided by r01, oops, and a ds right there at the end. Okay, so that's what we had at the end of last class. Now, what we're going to do now is to go on to the what's called the Kickoff formulation of diffraction by a plane screen. And this is section 11.4. So Kickoff formulation of diffraction by a plane screen. Okay, so what we have is that we have some point P naught here, and our goal is to find the disturbance of that point P naught. And over here at the left, we have some diffracting screen. Okay, which I'll draw like so. And we have some light, some radiation, maybe I should say, coming in from the left. So we have some wave coming in this way. And what we're going to do, we have to go through this integral here over some surface. And part of that surface is going to be this open portion here. That's how light's getting to this point. We'll call that open portion sigma here. And so what we're going to do is we're going to make a surface here that is supposed to be a circle, and hope you believe that that's a circle. Anyone doubt but what that's a circle? Okay, well, good. Circle here of radius r, and we'll come over here to some point on this open portion here, which I'll put in blue maybe. So this is the R01. The outward normal here is going to be like so, N. And this surface along here is going to be called S1. And this is going to be S2 out here. So the total surface here is S1 plus S2. Okay. Now you see why most of my drawings I do on the computer before I come to class. So we have to solve this integral equation here. And so we have that u p naught 1 over 4 pi integral over this surface of S1 plus S2. And what the real equation was we had here was partial of u with respect to n times g minus u partial of g with respect to n ds. So we're going to try to integrate this over this surface S1 plus S2. And so I'll slide this out of the way, but remember it, having a note so you have it in Goodman's book. And so G here, we had picked last week, or earlier this week I should say, of e to the ik R01 over R01. On S2, S2 being this portion of the circle here, since it's a nice circle, it's just e to the I, k, r, the radius of the circle, divided by r. I'm kind of thinking ahead, maybe you can guess what's going to happen to r, but we'll worry about that later. Not much later, but a little bit later. And so partial of g, well, on S2, g is equal to this. Okay. And so partial of g, with respect to n, is what? Just ik minus 1 over r e to the I k r over r. Okay. So that was fairly easy because S2 is just that portion of a circle. And furthermore, if we let r become large, this is going to become I, K, G for large R. Okay. So we can go back to this integral here, and I'll just do the integral over S2 for the time being, and then we'll come back to S1. So the integral here over S2 of g partial of u respect to n minus u partial g with respect to n. So that's I, k, g over ds. It's going to slide out of the way, is equal to, well, what I'm going to do, since this is a portion of a sphere, and it subtends some solid angle, I will just integrate over this solid angle, omega. So omega is the solid angle subtended by S2 at P naught. So we have the integral here over this solid angle of G partial of U respect to N minus I K U, and we're doing this over a solid angle, so it'd be R squared and the angle, the omega. Okay. And I'll celebrate getting to that point by having a sip of coffee. Now, I have to worry a little bit here about this integral. And we think here for a second, the magnitude of R times G is uniformly bounded on S2. And this integral here, I'll say therefore, this integral over S2 will go to 0 as R goes to infinity if U has the property that in the limit that R goes to infinity, R partial of U respect to N minus I K U is equal to 0. Now, this thing here is called the Sommerfeld radiation condition. And if we think about it, you know, when is this true? Well, it's satisfied if U vanishes at least as fast as a diverging spherical wave. Okay. So remember, U here is what we're using to illuminate the aperture. And so we're saying that if it vanishes, if U vanishes at least as fast as a diverging spherical wave, this Sommerfeld radiation condition is satisfied, and this integral is equal to 0. And we could think here that anything we illuminate this surface with really can consist, well, maybe it's a single spherical wave, or maybe it's a collection of spherical waves. And so this condition here is, we don't have to worry much about it being satisfied, because anything we illuminate the aperture with will be at least a collection of spherical waves. So we're going to get rid of this integral then. Go back here. We have gotten rid of the integral over this outer sphere here. And now we just have to worry about the integral over S1. Okay. So getting to the integral over S1 will take us to a next section here, which is going to be called, well, it's 11.5, and it's called the Kickoff boundary conditions. So our goal then is to figure out some way of integrating over this surface here, S1. And so what we're trying to solve here is U at P naught 1 over 4 pi, integral over S1, we got rid of the integral over S2, integral over S1 of partial of u with respect to n times g minus u partial g with respect to n ds. And we're going to assume here that this screen is opaque every place except for this area here where it's open, and we're going to call that sigma. Okay, so maybe I should write that down. Screen is opaque except for open aperture, sigma. Oops. Okay. Now we're going to make some assumptions here. And we'll call them the Kickoff assumptions. Just for the heck of it, I'll change color. So the first assumption here, not that you can tell a change in color, can you? But anyway, take my word for it. On this piece of paper, it's a different color. Okay. Across sigma, u and its derivative, partial of u with respect to n, are exactly the same as they would be in the absence of the screen. Okay, first assumption, across the open portion of the screen, u and its derivative, partial u with respect to n, are both exactly the same as they would be in the absence of the screen. That's the first assumption. The second assumption, then, according to Kickoff, is that over the portion of S1 in the geometrical shadow, of the screen, u and partial of u with respect to n are, what would you, if you were going to make an assumption, what would you guess they are? About 0, okay? So we're saying that, you know, over the open portion of the screen, u and its derivative, partial u with respect to n, are the same as they would be if we did not have a screen present. Over the portion of S1 in the geometrical shadow of the screen, u and partial u with respect to n are equal to 0. And then, if that's true, then we would have u of p naught is 1 over 4 pi. Now our integral simply becomes over the open portion of the aperture. And same thing as before, partial of u with respect to n times g minus u partial of g with respect to n ds. Well, we kind of like these assumptions because they reduce or simplify the result. But they're probably not entirely true, because probably this aperture does perturb the fields a little bit. And probably in the shadow here, there is a little bit of field left. And so this is, you know, these assumptions probably are not completely true. But it turns out that if the aperture is much greater than the wavelength. These, so we call fringing effects, can be neglected. And it turns out the two boundary conditions can be used to calculate or give results very, very close to experiment. Oops. Okay. So these two, assumptions, probably not 100% correct, but experiment will show that if the aperture is several wavelengths in size, the results that we're going to get from the theory that we're developing here agree very closely with experiment. Now, I should warn you that these two, I don't expect anyone to go through all this derivation without some notes or a book in front of them. But I do expect you to remember these two Kickoff assumptions. They're pretty important. And later we're going to come back to, we'll go to the Rayleigh-Sommerfeld formulation, which will not require these same assumptions here, but these are pretty important things. Okay, so what we're going to do now is that we are going to assume that these assumptions are correct, and we're going to go through here and calculate what the diffraction pattern, or what the disturbance, I should say, what the disturbance at point P naught will look like. And so this is section 11.6. A little more coffee. Okay. So 11.6 here. So we're getting pretty close to something of a lot of interest here. It's that Fornell-Kickoff diffraction formula, and it's going to be the Huygens-Fornell principle. So Fornell-Kickoff diffraction formula. And the Huygens-Fornell principle. Okay. Well, what we're going to have here is that generally R01 is many wavelengths. And so we're going to say that we're many wavelengths away from this aperture here. And if R01 is many wavelengths, then K, 2 pi over lambda, is much greater than 1 over R01. And just to refresh our memory, G here was e to the I, K, R01 over R01. So now, partial of G, respect to N, at point P1, say, is cosine N R01, so similar to what we did last class, I guess, times IK minus 1 over R01 e to the I, K, R01 divided by R01. So remember here that R01 is this vector from P naught to this point P1 on the aperture here, and that N is the outward normal here. And so this is about ik cosine n r01 e to the ik r01 over r01. So now we can take that and we can plug that back into our equation for u of p naught. And we get that u of p naught 1 over 4 pi integral over the open portion of the aperture right now, what we're looking at. E to the ik r01 over r01. Partial of u, respect to n, minus I, k, u, cosine n r01 ds. Okay. Now, I'm going to assume that we are illuminating this aperture here from the left, illuminating it with a spherical wave. And in real life, maybe it's more complex than that. It might just be but it would be just a combination of spherical waves. But let's say let u of p1 be the spherical wave, amplitude A, e to the ik r21 divided by r21. And maybe I need to do a drawing here again. And so we're illuminating this with a spherical wave from some point P2. And so that's our R21. And we have an outward normal here, N. And I don't know, point P naught is over here someplace. And this point right here that we're looking at is point P1, and this distance here then is R01. Okay. So we will now take this and plug it back into here, and I'm going to write down the answer, and I can't remember if I gave this as a homework problem this year or not. I did. Good. Okay. Because if not, I was just about ready to add another homework problem to your list. So you lucked out. Okay. So the interested student, or at least a student who would like to pass a course, will show the following. And what we're going to show here, u of p naught is a over I lambda, integral over the open portion of this aperture, e to the ik r21 plus r01 divided by r21 r01 times cosine of n r01 minus cosine, oops, better put a parentheses in there, minus cosine n r21, and never have enough space, ds. Okay? So interested student will show that that's true in his homework problem. And it turns out not to be very complicated to show that at this point anyway. What's that? I. I. Okay. Yeah, it does look a little... Well, it looks fine on paper. There must be some distortion in this TV system that's causing the problem, I guess. Anyway. So this is our result. We've been working very hard to get to this, so we'll celebrate by having some coffee, okay? And, I mean, this is true only for illumination by a single point source. But, I mean, it's going to hold for much more general illumination because any illumination you have really would be, can be thought of as being made up of a bunch of point sources. And this is what we call the Fornell Kickoff diffraction formula. Okay. Oh, yeah, interesting question. What is there anything in this interesting in this space here? Has anyone worked the homework problem to know the answer to this yet? 2. Okay. Thank you. Just checking, see if you're awake today. Okay. Well, one thing, I mean, this is, if we think about this for a second, this is kind of reciprocal. See if I can get both of these in here. I mean, this is reciprocal between P0 and P2. And so if I put something here, I get some disturbance over there. But if I put that something I put here, if I put it back there, I'm going to get the same disturbance back here. So it's reciprocal between these 2 points. So that's kind of interesting. And if we think for a second, just kind of stare at this for a minute, this is really going to be what we call a statement of what we call the Huygens principle. And let's see why that's true. And I'll move this out of the way, and I'll move this up here, but maybe I'll bring it back. So we're going to rewrite this. This is just going to be a mathematical statement of what's commonly called the Huygens, H-U-Y-G-E-N, apostrophe S, principle. And we'll rewrite this, and then you'll see what I'm talking about. So this mess that we had up here, we can rewrite that U of P0 is equal to the integral over this aperture of U prime of P0. We'll worry about what that is in a second. E to the IK R01 over R01 ds. And this U prime here is 1 over I lambda. We had an A. This is an I. I'll point that out again. Okay. A here. E to the IK R21 over R21. And then we have this cosine factor here. Cosine of n R21 minus cosine of n. This should be R01 and n R21. Okay, and not to forget my 2 here. So this is just taking this expression here and writing it in 2 terms. We had the integral over the open aperture of U prime e to the IK R01 over R01 ds, where U prime was all this other mess, 1 over I lambda, AE to the IK R21 over R21, cosine n R01 minus cosine n R21 divided by 2. And so what you can think of is that this disturbance we get here really comes from a collection of secondary point sources located within the aperture, and the amplitude here of these sources are very similar to the amplitude of what is used to illuminate the aperture, except that we have 3 changes here. So this is just, amplitude here is just what we use to illuminate the aperture, except for three differences here. And we have a 1 over lambda factor. So the say that the amplitude differs from incident amplitude by 1 over lambda factor. Okay, so that's one difference. A second difference that we have here is that the amplitude of these spherical waves, the amplitude here is reduced by this cosine factor. So the amplitude reduced by the what's called the obliquity factor, which is just the 1/2 cosine n R01 minus cosine n R21. Okay, so this quantity here is never greater than 1. Nor less than 0. Okay. And then the third thing, what have I left out here? Well, we have this I, 1 over I factor here. And so the phase of the secondary sources leads phase of incident wave by 90 degrees. Okay. So let's just go back here for a second and just restate this, because I don't know, this is kind of interesting the way this works out. That we're saying that if we calculate the disturbance at point P naught, what we're doing is we're thinking of the aperture of the system being filled with all of these spherical waves, like a Huygens principle thing, all these spherical waves. And the amplitude of these spherical waves is equal to the almost equal to the amplitude of the incident wave, except it's modified by 3 things. You have the 1 over wavelength factor, you have this cosine factor, and you have this 1 over I phase factor. Okay. So are you happy with the Fornell-Kickoff diffraction formula? Was all the pain and suffering we went through to get it worth it? Yes, question?
Do you need an explanation for why the secondary sources are 90 degrees out of phase from the...
No. The question is, do I have a good explanation as to why these secondary sources are out of phase by 90 degrees? And the answer is no, I don't have. I don't know. No one I know of. I have not seen a good reason for it. Anyone here want to come up with the own reason? It's interesting, isn't it? It's interesting. But I don't know that I can explain it. Doesn't bother us too much, but it's interesting it happens. Well, this, the Kickoff diffraction formula, Fornell-Kickoff diffraction formula, is widely used, and it works very well, works amazingly well, in fact, as long as the aperture is a few wavelengths, and as long as we stay away from the aperture several wavelengths. But there were these problems that we got into of making these assumptions, which definitely are not true, and so that bothers people. And so there's another formulation that Sommerfeld came up with called the Rayleigh-Sommerfeld formulation that's going to make it such that we don't have to make these assumptions. And let's go through that, and we're going to get a result that's very similar to what we have here. And in fact, in most cases, the only real change is going to be in this cosine factor here. And normally we talk about angles where we take this cosine factor to be equal to 1 anyway. So the result doesn't change too much. But let's go through it here. So what does, you have Goodman here. What does Goodman say about this 1 over I? Does he have anything great to say in there about it? No, that's what I was afraid of. Good, interesting question now. So Rayleigh-Sommerfeld. So we had these assumptions, and the real problem was that we had to impose these boundary conditions on both the field strength and its normal derivative. And so with Kickoff theory, had to impose boundary conditions on both field strength and its normal derivative. And there's a theorem, in fact, there's a theorem that says if a two-dimensional potential function and its normal derivative vanish together along any finite curved surface, then the function must vanish over the entire plane. And so these, this is a little disturbing maybe. So what Sommerfeld did was he came along with a different Green's function that is not going to make us have both these conditions on both the field strength and its normal derivative. And so we're going to look here at the new Green's function that Sommerfeld came up with. So just going back here, writing down our equation that we're working with. We had this integral over S1 of partial of u with respect to n times g minus u partial of g with respect to n ds. And this was, just write down when this was valid or what assumptions we made. And so to get to this, we had assumed basically three things. We assumed that the scalar theory is valid. And this was, we said earlier, really assuming that the diffracting apertures were many times the wavelength. We assumed that both U and G satisfied the wave equation. And we assumed that this Sommerfeld radiation theorem was valid. So we got rid of the rest of the integral here. Sommerfeld radiation theorem valid. And so now what we're going to do is we're going to think for a minute, and we're going to pick a new Green's function. And we're going to pick a Green's function. We'll pick Green's function such that either g or the partial of g with respect to n vanishes over S1. Okay? And that, kind of thinking back to how we went through this derivation, is we think back, we'll see that, if g or partial g with respect to n vanishes over this integral here, then we no longer have to have conditions on both u and partial of u with respect to n. So then we'll not have to have boundary conditions on both u and partial of u with respect to n. And then the inconsistencies in the Kickoff theory will be eliminated. Okay. Okay, so now we're going to pick a new Green's function, and with help of Sommerfeld. And remember, let's see, before the Green's function was just a spherical wave. And what we're going to do now for our Green's function is we're going to pick two spherical waves. Two being better than one, I guess. So let's see what we have. So, any questions on that, or? Okay. So I'll just repeat it here that that we're going to pick a Green's function such that either the Green's function or partial g with respect to n will vanish on S1. And if this is true, then we're not going to have these boundary conditions on both u and partial u with respect to n. And then these little inconsistencies in this Kickoff theory will be eliminated. No, this is not correct for the assumption that you're far away from the aperture and that the aperture is small, is large compared to the wavelength. We still have these restrictions. Okay. Well, I don't know that I'd say they're bigger problems. I mean, these boundary conditions, if they really messed up things, were always wrong, okay? And here, we're just saying that we're, to really handle small apertures, we have to go to a vector theory. And the changes will not be enormous, but there will be some changes in the irradiance in the diffraction pattern. This is still pretty general, and you're not going to find a lot of situations where this theory will not satisfy your needs. It's amazing. All these approximations used to bother me. You had all these approximations you're making. How can you end up with something that gives you anything that makes sense? But I don't know, somehow all these approximations just kind of work out, and the end result that you get here agrees amazingly well with experiment. It's, maybe I read someplace that someone was saying God was apologizing, making the problem so difficult for you that he made it so you could make all these assumptions, still get the right answers. I don't know. Maybe Gaskell told me. I forget who it was, but I read that someplace. Okay. Anyway, let's go to this new Green's function here. And we have something over here, P naught, and call this line here. And we have an outward normal here. And, you know, speaking of Gaskell, I have to tell you, he's always so funny, I think. I saw him late yesterday, and he looked terrible. He said he was on the way to the emergency room. He had been playing Frisbee with the young students. And did any of you play with him? He looked terrible. But he said all this exercising, he realized all this exercising, you know, helped his heart. And so they reduced his chances of dying of a heart attack. But that meant his chances of dying of cancer were increased. So I wasn't sure that it was worth it. I don't know. Anyway, I have a lot of fun with him, I have to say. So we'll pick this other point over here, and I call that P naught with a little tilde over it. And this is R naught 1 with a tilde over it, and this is R naught 1 here. And maybe I should have a little vector there. Okay, and so what we're going to do is our Green's function here. It's actually two of them we can pick, but I call this G minus, okay, at point P1. So this is P1 right here. That this is equal to e to the I k R01 over R01 minus e to the I k R01 tilde over R01 tilde. So now our Green's function is going to be not one spherical wave, but we're going to pick two spherical waves. And for the G minus Green's function, these two spherical waves are out of phase, 180 degrees. That's why we have the minus sign here. And they're going to become mirror images of one another. Okay? So these are mirror images of one another, and these are, right now, out of phase by 180 degrees. And so now, disturbance at P naught here is minus 1 over 4 pi. Integral over this aperture of u partial of G minus respect to n ds. And this is sigma. And we're going to call this the first, oops, if I could write, first Rayleigh Sommerfeld solution. The second solution will be when this is a plus sign instead of a minus sign. Okay. And so now we need to go through this little calculation here to see what we get. So we'll slide this up. And so the partial of G minus respect to n at point P1, I won't put that in here, is just like what we had before, but it's going to be a cosine n R01 times at I k minus 1 over R01 e to the I k R01 over R01 minus cosine n R01 tilde. Okay. IK minus 1 over R tilde, R01 tilde. E to the I k R01 tilde over R01 tilde. And if we go then to a point on this surface here, these lengths are going to be the same since one is a mirror image of the other. And so for P1 on the surface S1, R01 is R01 tilde, length of it here. And the cosine of N, R01, is minus the cosine of N, R01 tilde. And so, going back to this expression then, partial G with respect to N, partial G minus respect to N, is then 2 cosine N R01 IK minus 1 over R01 e to the IK R01 over R01. Okay, time for more coffee. And I mean, we're going to assume that R01 is many wavelengths. And so this term right here will become partial G minus respect to N is 2 I K cosine N R01. And then we simply will have e to the I K R01 over R01. And if we go back to what we have, how does this compare with what we got for Kickoff? What? It's twice. This is twice what we got for the Kickoff analysis. So this is 2 times what we got for Kickoff. Okay. So I'll leave this for just a second, and then we'll come back to it. If we go to instead of having these 2 spherical waves out of phase by 180 degrees, let's put them in phase. And so in that case, we will have what we'll call a G plus. And so that's e to the I K R01 over R01 plus e to the I K R01 tilde over R01. And if we go through this derivation, taking our derivatives and whatever, what can you see what's going to happen to the normal derivative? Yeah, it's going to go away. So maybe the interested student will go through it, but it's pretty straightforward. It just drops right out very nicely. That now when we go through this, finding the normal derivative, it's going to vanish. Okay? And if we also look at it, it's going to turn out that G plus is twice the Kirchhoff-Green's function G. So for the positive case, the the G plus will be twice what we got for Kickoff, and the normal derivative is going to vanish. Okay. Now, let's go back then and put this into our equation for diffraction and see what we get. And so I'm going to, I will go back first to the G minus Green's function and put that into our expression here. So now we have that U of P naught is equal to 1 over I lambda integral over S1 of U of P1, this U, e to the I k R01 over R01 cosine n R01 ds. Okay? And I guess the only assumption here, big assumption, was we assumed that R01 was many wavelengths. The thing now is that we only need to apply the Kickoff conditions to U alone. So now only need to apply Kickoff assumptions to U. Okay. And so what we will get when we apply those assumptions to U is what? This same equation, except, I'm going to make life simple for me, except it's just over the open portion of the aperture. And so the boundary conditions that before we had to apply to partial U with respect to n have gone away. And so the inconsistencies of the Kickoff theory have been removed. So we can go on here and if we, instead of using the G minus, if we use G plus, now the result that we're going to get here is that U of P naught is 1 over 2 pi, summation here of partial of U respect to n, e to the I k R01 over R01 ds. Okay. So again, let's go back and look at what illuminate this aperture with a spherical wave. And so U of P1 will just be A, e to the I, k, R21 over R21. And we plug that in here. And for the G minus Green's function, we will have that U of P naught is equal to A over I lambda integral over the open portion of the aperture e to the I k R21 plus R01 divided by R21 R01, and we'll get the cosine here. Cosine between n and R01 ds. And I guess to stick with Goodman's notation, he'll call that answer 1 here for the G minus. And if we use the other Green's function, the G plus, running through here. So use G plus. We'll get what he wants to call answer number 2 here. And that's going to be a minus A over I lambda, integral over the aperture of e to the I k R21 plus R01 over R21 R01 cosine of n R21 ds. Okay. So these are the two results that we got here for the using the negative Green's function for the two spherical waves that are 180 degrees out of phase, and the positive Green's function. And the difference is, well, there's a minus sign here, but that's taken care of by the fact that the angle between the n and the R2 is greater than 90 degrees. So we get a cosine n R01, cosine n down here R21. And so it's kind of interesting to compare these results. And we can just kind of write that down here. I'll go to a clean sheet of paper. Compare the results that we got for Sommerfeld with what we got before for Kickoff. I'll move these out of the way, but I won't forget what they are. So what we can say is that in general here, we got a result that said U of P naught was equal to A over I lambda, integral over the open portion of the aperture, and we got an e to the I k R21 plus R01 divided by R21 R01. And then we get another factor here I'll call psi ds. We got this same result for the Kickoff theory, and we got it for Rayleigh Sommerfeld, both Green's functions. The only difference is what this psi is here. And so the psi, if we write down here, that if we go to the Kickoff theory, that was equal to 1/2 cosine n R01 minus cosine n R21. And that's Kickoff. For Rayleigh Sommerfeld, we got here, well, we had a cosine of n R01 and that was the Rayleigh Sommerfeld and that's where we had the G minus Green's function. And when we had a G plus Green's function, we had a minus cosine n R21. That's Rayleigh Sommerfeld. Number 2. Okay. And if we think here for a second, well, the Kickoff is simply the average of these two Rayleigh Sommerfeld ones. Kind of interesting it turned out that way. Okay, so they both gave pretty much the same result. Kickoff was the average of the two Rayleigh Sommerfeld solutions. And of course in real life what happens? Normally we work at such small angles, all these are equal to 1 anyway. So it doesn't make much difference. I'll say often work at small angles. So this is equal to 1. Okay. Any questions at this point? So how many of you are going to go back and get out Goodman's book and study this? Everyone. Good, I hope so. It's very well written in there. You can even read his writing better than, you can read his typing better than my writing. His drawings are nicer. Okay. Well, that's the basic theory of diffraction here. And in the next chapter, we're going to go through and make some even more approximations and get to what we'll call the Fornell diffraction and Fraunhofer diffraction. But before we go to the next chapter, we have a couple of items I want to cover yet in this chapter. And the first one, which I can just barely start with here, I won't say much at all because it's once we get into it, it'll take a while. But it's something that's called the plane wave spectrum approach. And actually, this is my favorite approach to diffraction, I have to say. And the first time I heard about it was in Goodman's first book, which came out in '68. And it's funny, you go back and look at it, he almost apologizes for bringing this up for some reason, I don't know. I think mainly because it wasn't very widely discussed before that. And the Kickoff and Sommerfeld is the way that most people look at it. So he brings this up in his first edition, and it's really very clever. And it turns out it goes back quite a while, and if you check Goodman's book, I guess the first reference I see on this is by some author by the name of Ratcliffe. And I won't give you the whole reference, but it dates back to 1956, so it has been around a long time. And what I like about it is that first it goes back and uses all these crazy Fourier transforms that you had to suffer through last semester, so I'll give you a chance to make good use of them. But as we go through it, there's a very nice physical explanation as to what's happening, and that maybe is a complaint I would have of a lot of what we've covered so far in diffraction, is that there's all this algebra, and it's not, I won't say it's difficult algebra, but there's a lot of algebra and not a lot of really physical explanation as to what's happening. Next class, when we go through this plane wave spectrum approach, we have a little algebra we'll go through first, but then when we get done, we'll look back and say, I understand physically what's happening here. So it's going to be pretty neat. So with that, I guess I will stop. You have 2 basketball games to concentrate on, plus maybe a little diffraction you have to study. And so I'll see you bright and early next Tuesday morning.